It's my pleasure to introduce our first speaker. Professor Younan Xia is the Brock Family Chair and Georgia Research Alliance Eminent Scholar in Nanomedicine at the Georgia Institute for Technology. He received his PhD degree in physical chemistry from Harvard University under George Whitesides and started his academic career at the University of Washington. After a stop at Washington U in St. Louis, he and his group settled at Georgia Tech in 2012. Professor Xia's group has invented a myriad of nanomaterials and with well-defined and controllable properties for applications related to many fields: plasmonics, catalysis, fuel cell technology, electronics, photonics, and regenerative medicine. Today, he will share with us the concept, success, opportunities, challenges of nanomedicine. Please join me in welcoming Professor Younan Xia.
And I'm glad to be here because Georgia Tech is also part of this NSF-sponsored network. So I'm going to give you a very brief introduction to nanomedicine. And so let me start with a slide. You might have seen it, at different occasions. So basically it shows a summary of different stuff we are familiar with and at all different scales. And the message is nano is important. People are interested in moving from bulk, large scales, eventually to this very small scale. And depending on who you ask, you may get different answers. Why nano is interesting? What's the motivation, right, to work on nano? And if you ask engineers, they think if we can make things into smaller scales, you can put more devices on the same chips, so you can have more powerful computers, so on and so forth, right? If you ask physics, they will tell you it's exciting to look at the small structures. You can have quantum effects. You can tune their properties by controlling their size and dimensions. If you ask chemists, they say, if you move to small structures, you may also observe new properties. And in particular, for catalysis, if you can make things as tiny as possible, you can increase the specific surface area, right? So you can have very high mass activity for the catalyst. And for biomedical applications, actually, the reason or driving force could be a little bit different. So I hope you are going to learn from this lecture today. So before I get into detail, let me show you a list. This is like a table of some of the most popular drugs, used to fight cancers. So typically, as you can see over here, we can divide them into three categories, like hydrophobic ones, hydrophilic ones, and those with very high density of charges. And most of them are basically small molecules. So in a sense, it's going to be quite challenging if you want to deliver these medicines to the specific site of interest, like the malignant cells, diseased tissues, and so on and so forth. The reason is simple. For example, if you have hydrophobic drug molecules, they are not going to be mixed very well with your bloodstream, right? Because your bloodstream is kind of like water-based. So in this case, you may have aggregation issues, and eventually you're going to have a delivery issue. And even for those molecules that are hydrophilic, looks like they can be put in water very nicely, but those molecules may have a problem to enter cells to do the function. So in this case, it's going to be also troublesome. So basically, if we want to understand why we want to look at nanomedicine, we had to start with the basic structure of biological system, the cells. So cells can be considered as something with dimension about 5 to 10 microns, all right? What's most important, of course, is the plasma membrane. That's actually the most important component to create a life. Without this membrane, actually, you have no way to create a life because you have no way to control the functions, what's going on inside, and eventually you can regulate the behavior and functions. And as you have learned probably in chemistry or biochemistry, right, the plasma membrane basically is a bilayer structure made of lipid molecules. I'm going to show you some more details later. And basically, this membrane okay, is very dense packed. So in a sense, it's going to form a very, very nice barrier. It's so nice, basically small molecules won't be able to go through it freely. Okay, you are going to be regulated. So basically, here just show you kind of like a summary how small molecules are able to go through these very thin membranes. Overall, the thickness is only about like 5-6 nanometers. It's not very thick, okay? But again, it's very tight packed for these lipid molecules. And for small hydrophobic gas molecules, they have a pretty high chance to go through by diffusion. There's no issue over there. And then try to move to like hydrophilic molecules like water, like ethanol, and so forth. They can also have a chance to diffuse through, but the rate will be slower. So basically, this is the order. Okay, you're going to have a reduction in terms of diffusion rate. And then if you go to larger ones like amino acids, okay, it's a major component in the critical component for making proteins, enzymes, so on and so forth. They are going to have very slow diffusion rate through membrane. It's going to be highly regulated in a sense. And for ions, that's used to for signaling and audience purposes, they have to be tightly regulated. Okay, they have to basically go through these ionic channels and so on and so forth. So here is just give you some specific numbers, give you some idea, how fast, how slow these molecules can go through this very, very thin physical barrier known as plasma membrane. And again, as you can see on top, these kind of small molecules, you have pretty high permeability, and then move down with larger size, even though they are still hydrophilic, okay, they are going to have problem to go through, and also hydrophobic molecules too, they have an issue to go through. And in this case, if we have a drug molecule, okay, like shown over here in this table, okay, if you want to deliver them into the cell, and in particular, sometimes you have to deliver them into the nucleus, and then it's going to be very challenging. Okay. Overall, it's very hard to achieve a high enough concentration. Eventually, you're going to have the function you expected. So that's why we had to think about a better way to basically to achieve better delivery for these small molecules. So on the other hand, I just want to point out there's another way for small molecules to get into cells. This is known as pinocytosis, or simply like cell drinking. Okay, so the membrane can always have a chance to form this inward ingranation, and then whatever in this area will be uptaken by the cells, and eventually will be processed inside the cells. But there's an issue over here. This kind of process, as listed, as highlighted over here, is non-specific. So basically, that means no matter it's drug molecules or nutritions or other things, all of this just passively being uptaken by the cells. Okay, so in a sense, eventually the concentration of drug molecule inside cells could be still pretty low to have the function you want to achieve. At the same time, the selectivity issue is going to be important because for drug molecules, you only want to deliver them into malignant cells, cancer cells, for example. You don't want them to go into healthy cells to kill healthy cells, right? So in this case, of course, this is not going to be an effective mechanism. And also, if you want to achieve high concentration of drug molecule inside cells, you also have very high concentration of drugs in the outside food. That's also going to be a challenging, actually, in this case. So that's why people start to look at the cells again, actually realize that there's some functionalities of cell membranes actually that can be utilized to achieve both selectivity and high efficiency or efficacy. So in this case, we can look at these receptors that typically overexpressed on the plasma membranes. So depending on the disease, actually you might have specific type of receptors, okay, that's going to be overexpressed. And this could be used as a mechanism for targeting purpose. So you can somehow have a drug molecules and somehow related to some kind of ligand. That ligand can have specific binding interactions with these receptors, and then it achieve a very high specificity in terms of delivery. So that's basically the major driving force for nanomedicine, or the motivation, or the rationale for nanomedicine. And in this case, of course, it's not going to be very effective if you just use small drug molecules individually. Instead, you are going to package them, into nanoparticles, and then you through these nanoparticles you deliver them into the cells, and then you can achieve a high concentration inside the cells. Eventually, you can kill the cancer cells as you want. So that's basically the idea, and this idea, of course, is not really like new, right? Because in our body we use it already for thousands of years, probably. In this case, I'll just show you how we handle small molecules like fat, like cholesterol, this kind of small molecule. You can also consider them as drugs in a sense. And in this case, you don't really have a high concentration of these small particles in your bloodstream. Instead, you are going to pack them into some nanoparticles. This is known as lipoproteins. Here I just show you one example. Is low density lipoproteins, LDL actually. As you can see, the diameter is only about like 30 nanometers. It's already very small. In the nano regime. And what you have over here is you have high density of this fat and cholesterol going to be packed densely inside. And then on the surface, you are going to have this lipid monolayer. It's not a bilayer in this case, because what you have inside is hydrophobic. So you only need to have a monolayer put on the surface. And what's also important is to have this lipoprotein B100 actually. This is actually the ligand I mentioned earlier. This is the chemical or biological motif actually that can interact with the receptors on the cells. This is called the LDL receptor. Basically, you can imagine these particles will move around in the bloodstream. And whenever the cell needs this fat and the cholesterol, actually both of them are also important species or components in our body, right? This, of course, can be used as lipids to make cell membranes. At the same time, like this can also serve as source of energy too, fatty acids, of course. And in this case, if the cells need these kind of components, they are going to express these receptors on the surface. And then when the particle move close to the vicinity of this surface, they are going to have strong binding, basically. Once they have strong binding, they are going to trigger endocytosis, actually. And then this LDL particles will get to endosome and then lysosome and will be processed. And then they are going to take whatever they need, like amino acids, cholesterol, and so on and so forth, used by the cells. And they can also recycle the receptors on the surface of these particles. They don't necessarily generate new ones. They can always put them back onto the cell membrane surface and then reuse it. So this is a very efficient mechanism. Can reduce, of course, the concentration of these highly hydrophobic molecules in the bloodstream. Otherwise, you're going to have trouble, actually. So that's why the concentration of these molecules need to be highly precisely and regulated. If you have like deficiency for LDL receptor and so on and so forth, you have to take a medicine, actually, to regulate that. Anyway, so basically this shows us a very good idea, how we can deliver these kind of small molecules into the cells. Through this receptor ligand receptor specific binding. So that's basically the core concept for nanomedicine. It's basically similar idea. When you deal with different types of diseases, you only need to worry about how you can find out the receptors. We used to refer them as biomarkers, and then you can engineer your nanoparticles. You can put some specific ligand on the surface for the targeting purpose. So that's basically kind of like a straightforward concept. But in reality, of course, there are many complications I'm going to discuss later. So most of these slides, actually, I'm going to talk about in the next half hour are mainly taken from this review article we published a few years ago in Agricultural Chemie. If you are interested, you can take a look at it. So basically, we reviewed how nanoparticles could be engineered for drug delivery purpose related to cancer nanomedicine in a sense. So basically, as summarized over here, when we talk about nanoparticle platform, we have to think about a number of parameters or handles you can use to engineer their properties. This includes the size, of course. You have to have a way to manipulate the particle size for specific applications. And the shape is also going to be kind of important. Okay, I'm going to show you some examples later. And then, of course, the type of materials. You can have something that's very biocompatible, or maybe just something completely taken out from your body, or like a liposome and the proteins and the antibody conjugate and so on and so forth. You can also have very exotic materials like polymers, like maybe even carbon nanotubes or inorganic nanoparticles and so on and so forth. Basically, just show you all the diversity of materials that could be really think about. You can really consider, okay, when you engineer the nanoparticles. Of course, at the end, I'm going to mention not all of these materials are good candidates, actually, okay, because right now the fashion in nanomedicine, okay, is you take whatever materials people have developed in the lab for many or different other purposes, and then just inject them into mice and do biomedical application. That may not be the best approach, I have to say, but at the moment, actually, that seems to be the fashion, okay? And in the future, of course, when you really want to have something promising for commercialization or clinical use, you really have to think about how you can start with some materials that's completely biocompatible, biodegradable, and then engineer them for the specific application. That probably will be the best option or approach we should take. And then, of course, the surface is always very important. You have to have the right functional group on the surface, and then you can initiate the right interaction with cells, okay, and then you can achieve your goal. So in this case, this may include pegylation. That's very important if you want to have your particles somehow in the being able to transport in the product stream without being taken by phagocytes. And also the functional group that could help you to make further bioconjugation to put the ligands onto the surface. And this could be into like peptides, proteins, antibodies, and so on. There are many, many different choices, okay? So that's a very broad area of research. And sometimes you can also change the surface size or densities, and that could also give another handle to manipulate their behaviors in vitro and in vivo. Okay, so let me just show you some examples. So in particular, I want to take 3 examples of materials, okay, to demonstrate some of the concepts I just mentioned. And I'm going to start with liposomes. Okay, that's basically the most successful carriers for nanomedicine. Okay, most of the drug systems are based on formulations are based on liposomes, and then I'm going to talk about the phase-changing materials, and then finally talk about the very exotic materials, gold nanomaterials. Actually, our body don't even know how to digest or degrade this material yet. Okay, so in that case, it will be a different category of biomaterials. In that case, it's completely bio-inert, but they cannot be bio-degraded. So let's start with liposomes. Basically, I took some of these slides from my lectures when I was teaching freshman chemistry and also the biomaterials class at Georgia Tech. So for those of you who are not familiar with liposomes, lipids, and so on and so forth, here is a good starting point. the bubbles, all right? I'm sure you have played with bubbles in the childhood, right? Hope you still remember it. So basically what's amazing about this is you have to use surfactants. Surfactants basically shown over here as an example. You can have a hydrophilic head with a relatively long hydrophobic tail. So that's the basic requirement to make a good surfactant. So for these molecules, you can imagine this hydrophilic head can be polarized by water. Basically, they like water molecules. They can interact very strongly. And then this hydrophobic tail, of course, they hate water molecules. They want to shy away from water molecules. So now if you put them in water, what they are going to do, well, they are going to form their own structures to deal with the problem. And basically, the bubbles you are generating over here is quite a remarkable structure. The thickness overall, okay, is only made of two molecules. Basically, it's about like a bilayer thickness of the each one of these surfactant molecules, and in between you are going to have water molecules being trapped. Okay, so this is like an inverse structure if you are going to compare with the cell membrane structures I'm going to show you just 1 second. And in this case, the hydrophilic head is in contact with water molecules, and the hydrophobic tail is going to be exposed to air, because air is hydrophobic stuff, okay? So it's different from water. And at the beginning, of course, you may have a lot of water molecules trapped over here. You can make pretty big bubbles, but eventually the water will evaporate, and the bubble will become smaller, eventually will collapse. Okay, so basically that's the idea. The bubbles can also have colors, but they are different from the conventional mechanism based on pigments. Just want to point out for fun. And in this case, this is really due to the light bounce back from the outer surface and inner surface of this bubble, okay? And then generate interference. So that's why I gave you this pretty colorful appearance. Anyway, so that's just for introduction purpose. And in our body, actually, we have some surfactant molecules known as lipids. And here are three major categories are shown over here. And the first one is called phospholipids. And in this case, you are going to have a phosphate group instead of the carboxylate group. Okay, I just showed you on previous slide. And then you also have this hydrophobic tail. Okay, so that's very similar, okay, in terms of composition. And you can also have glycolipids. Basically, you have going to have a sugar unit attached to it. And also cholesterol is a third class of lipids, actually. So in this case, you have the hydrophilic hydroxyl group, and then we have very big hydrophobic tail or unit attached to it. And taking these three different combinations of these lipid molecules, you are going to be able to build these plasma membranes, okay, as shown over here. So basically, you have this bilayer structure, but this bilayer structure is going to be opposite to the bubbles I showed you on previous slide, because the hydrophobic tail are going to next to each other, and you don't have anything trapped between them. And the hydrophilic head is going to be exposed to water environment. Okay, inside of cell you have water, outside of course you have water. So basically, by forming this particular arrangement, you can make the head group and the hydrophobic tail happy. Okay, they don't have to meet people they don't like, right, in a sense. So basically, you also need to include ionic channels, as I mentioned earlier, in order to regulate transportation of those ionic species, right? And also you need to have these cholesterol molecules being included, because cholesterol molecules, as you can see, it has a pretty hard, rigid and hydrophobic component over here. Basically, can make the membrane pretty rigid. Okay. Overall, the cell membrane is a pretty fluidic system. Okay, it's a very dynamic system, it can be changing all the time. But sometimes you might want the cell membrane a little bit stiffer. What are you going to do? You can add high concentration of cholesterol molecules into it. Okay, so basically, in biological system, we already developed all these different mechanisms to adjust the mechanical properties of cell membranes, and of course, eventually the permeability and everything are associated with it. So here is another example, okay, just a different view of these lipid molecules. And different from the surfactant molecules I showed you earlier, you have phosphate, and also you are going to have 2 tails instead of 1. That's also common. This is, again, basically for the purpose of making a large structure like cells. It's about like 5 to 10 microns in diameter, okay? So in this case, it will be advantageous if you have this 2 tails instead of a single tail, because otherwise, if you have a head that's bigger than the tail, it's hard to pack them actually when you form these bilayer structures. Anyway, if you take these lipid molecules, if you try to dissolve them in water, what they are going to do, well, of course, it's tricky, right? Maybe at a very low concentration, you can get them dissolved, but once their concentration becomes high enough, they won't be able to dissolve anymore, because eventually this hydrophobic tail will say no, okay, to this process, because they don't really like water molecules. So what they're going to do, they start to form these self-assembled structures you might have heard about, like my cells. This is just you have like a spherical structures. You have this hydrophobic tail embedded inside. You have this hydrophilic head on the outside. This is just the cross-sectional view of my cells. But if you keep increasing the concentration of these lipid molecules in the water, eventually they're going to form something we call liposomes or vesicles. This is a bilayer structure. It's very similar to the plasma membranes I show you, but this is a very compact structure. Typically, it's only about hundreds of nanometers or maybe tens of nanometers in diameter instead of micron scale. Okay, and again, in this case, you have this bilayer structure. You have hydrophilic head inside, hydrophilic head outside, and you can have water content inside and water content outside. Basically, that's kind of structures, and well, that may not be so important. Let's just move on. And it's pretty easy nowadays in the lab to form these liposomes. Okay, so first what you need to do is to just dry your lipid solutions to form these so-called lipid films. Basically, just a bilayer stacking of these molecules. And then you add water, you sonicate them. Basically, you can just do exfoliation, actually. And eventually, these molecules can be peeled off from the surface and generate these vesicles, okay? And depending on the size of these vesicles, we have different names. Like SUV means small unilamellar vesicles. And this LUV is large. It's just a difference in terms of diameter. And the structure is very similar. It's the bilayer structure. That's the kind of typical thing. And nowadays, you can easily get the recipes from a company. There's a company selling all different types of lipids. If you're interested, you can go to their website to take a look at it. And basically, if you do sonication at the same time, if you have some drug molecules in a solution, and whenever this layer is peeled off and then fold, and some of these drug molecules will be encapsulated naturally. Okay, so basically you're going to form these encapsulated liposomes with drugs loaded inside. And this, of course, works best if you have hydrophilic drugs, all right? That means the drugs have to be soluble in water, like in this case, it's glycine, actually, okay? So overall, here is something you can imagine, okay? This is a cross-sectional view of the liposome. Inside, you may have whatever hydrophilic stuff. Okay, this could be particles, nanoparticles, and it could be molecules, it could be drugs, could be whatever things, okay, you are interested. It could be dye molecules and so on and so forth. And that could be easily encapsulated inside this liposome during this sonication process. And now, of course, you can also add functional group to the outer surface. And in this case, this could be for the targeting application. And for hydrophobic drugs, unfortunately, this platform does not work very well because inside it is hydrophilic hydrophilic, right? You cannot imagine to have hydrophobic molecules sitting inside. Instead, this hydrophobic molecule or drug molecules could be loaded into the bilayer structures, because after all, this bilayer zone is going to be hydrophobic. But of course, the loading capacity is going to be relatively low, because after all, this membrane is only about like 6 some nanometers thick. Okay, the amount of drug molecules you can load it over here is quite limited. Anyhow, if you look at the nanomedicines currently in use at the clinics, basically most of them are based on liposome formulation, okay, as you can see over here. And of course now you start to get into other materials like polymer-based particles, and even there are some inorganic nanoparticles that are also being evaluated for clinical application. Anyway, if you're interested, you can take a look at some detailed discussion in our review article about this table. Okay, that's basically, yeah, I'll show you most of the drugs that have been approved by FDA for treating cancer patients. Okay, there are quite some in the pipeline come up in the near future. So now let me switch gears to the second type of materials I promised. So in this case, it's so-called phase-changing materials. Phase change, well, phase is something related to physical status, okay, or physical state of a material. And the common example as shown over here is the 3 different states of water, right? You can even have 3 states coexisting actually at the same temperature or on the same condition. So you have water, liquid, you have solid, ice, and you have vapor in the cloud in this particular case. So what's phase-changing material? Well, if you think about these 2 different phases, you can always have phase transitions if you change the temperature of the system, right? So for example, if you heat ice to temperature above 0 degrees Celsius, the solid will start to have phase transition to become liquid. You're going to have a melting process. And on the other hand, if you cool down this liquid, you can have this opposite phase transition. So this is what we refer to the phase change of behavior. And here is the typical plot of temperature versus the heat, okay, involved in this process. And if think about the solid to liquid phase transition, for example, typically they are going to occur at a specific temperature. Okay, like for ice, it's going to be at 0 degrees Celsius. If you move to another solid material that may be 10 degrees Celsius and so on and so forth, you are going to have very well-defined melting point. And during this melting or solidification process, you are going to have a lot of heat being exchanged, okay, with outside and either absorbed or maybe released. That's going to be something we call latent heat involved. But before all of these materials are being transformed into other phase, this temperature is not supposed to change. The temperature will be basically stabilized at a specific value. And there are a number of unique features for phase-changing materials. Basically, you see this fixed sharp temperature at which you are going to have phase transition. And then you have a lot of heat or energy being involved. And another thing that's actually very important for biomedical application, in particular like drug release and drug delivery control release applications, is a huge difference in terms of mobility. If you think about the molecules in the solid ice, there's no way for them to move around. Okay, everything is going to be pretty much fixed at whatever location they were put. Okay, so the mobility is going to be very low. But once you put them in a liquid matrix, of course, the drug molecules can come out much more easily, okay, than in the solid state. And in the gas phase, of course, even faster. So you can see the huge difference in mobility. So that means you probably can use this phase transition as a way to gate the release of drug molecules. So that's basically the concept we have explored. So here's the idea, just show you the mobility difference. If you put butter over here, before you melt it, it's a solid. It will stay there, whatever shape you put them, okay? It could be hot, right? But once you start to melt it, liquid will just go away very easily and quickly. So you can see the mobility difference. So in a recent study, we have focused on one unique system based on fatty acids. Why we want to use fatty acids? Because they are completely compatible and biodegradable molecules. Basically, they can be taken from our own body, actually. Okay, there's no toxicity or other side effects. And by taking lauric acid, shown over here with 12 carbon atoms, and stearic acid with 16 carbon atoms, and they have their unique melting points. One is at 69 degrees, another is at like 44 degrees, lauric acid and the stearic acid. If you mix them at the right ratio, in this case about a 4:1 ratio, basically you are going to form a eutectic mixture. That's going to melt at a specific temperature. This is going to be about 40 degrees, so just slightly above the body temperature, our body temperature, okay? So now if you can make them into nanoparticles, and then you can, here just show you an example, okay? You can put some molecules on the surface or ligands. At the same time, you can stick some dye molecules. We use dye molecules because eventually we want to trigger the melting with light instead of using direct heating. So these dye molecules can also be co-loaded with drug molecules inside these PCM particles. And then whenever we strike this particle with a near-infrared laser, that can be absorbed by this dye, and that will generate heat. Heat will basically raise the temperature of this system, eventually will melt this particle, so drugs will come out swiftly. So here just show you the example. This is after we have doxorubicin that can give us this red fluorescence, basically. This is before we do release. This is after irradiation for 80 minutes with a near-infrared laser. You can see the pattern is very different. Here you have a small kind of like a punctated structure. It's like small domains, because these particles are going to be put in endosomes, and they are going to be separated from each other. So that's what gave us this dotted pattern. But once these drugs are released, the drugs is released from the particles, they are going to be in the entire cytosol. Basically, it gave us this uniform fluorescent distribution. So basically, you can see the release. And you can also quantify this without the laser triggering. You don't have any release because the temperature of your body is below the melting point. Is about 39 degrees. However, if you have a laser irradiation, you can have a very quick release. So basically, we are trying to develop this as a useful platform for controlled release of drugs. So hopefully in the future, can be used for cancer nanomedicine and related applications. In a related study, we also take similar mixture, but we are going to put it back into a biological system I mentioned earlier. This is LDL particles. Basically, we want to use the targeting mechanism of LDL. They have this apolipoprotein B100, okay, that can bind to most of the receptors on cancer cells. So basically, we want to use this as a carrier. But we don't want to deliver fat and cholesterol, of course. We would like to develop anti-cancer drugs, for example. So in this case, we can remove those fat and the cholesterol inside and reconstruct it, actually, the inner core of this LDL particle. And basically, we can use the fatty acid mixture mixed with the drug and also the dye molecules. And then we can do release. And at the same time, we can also do targeting. Okay, so here is the idea. You can see this is the basically native LDL particles, and the size is about like 50 some nanometers. It's below 50. It's about 30 to 40 nanometers. This is 100 nanometer bar. This is the system we have loaded them with fatty acid and dye, and this is a system we have loaded them with fatty acid, dye, and anti-cancer drug doxorubicin. Okay, so you can see the morphology overall could be preserved during this reconstruction process. And also we have done some preliminary studies in terms of in vitro and in vivo evaluation. Okay, for in vitro, basically we compare these two different cell lines, one with LDL receptor, one without LDL receptor, one with LDL receptor on the surface. So you can see for these cancer cells, you can see the toxicity for these tox are loaded inside. And for the cells without these LDL receptors, eventually this could be an example of healthy tissues in your body. They don't uptake this reconstituted LDL particles, so they can maintain viable actually, okay, even at relatively high dosage we applied. And this is in some in vivo studies, just show you the melanoma tumor actually, that basically this is the blank, okay, this is the fluorescence image for the particles with the dye molecule being, basically we use coumaline actually dye, loaded LDL particles to do some imaging characterization. And with this dye, or not coumaline, I'm sorry, it's IR780. Okay, so in this case, you can see accumulation of these particles inside this tumor. Okay, and this is just at different time points. And the blocking means if you inject native LDL particles to block those receptors, and of course you don't see much accumulation of these reconstituted LDL particles anymore. So that's just some control experiment to show both in vitro and in vivo you might have some selectivity to help deliver anti-cancer drugs into tumors. So finally, let me show you gold nanoparticles. I'm sure you're going to hear some more presentations later about the other applications of gold nanoparticles. Basically, it's kind of amazing if you think about in a bulk gold. It's beautiful yellow color. If you make them into nanoparticles, they are completely different in terms of color. They become this beautiful ruby red color, and that was first observed by Michael Faraday, actually, more than 150 years ago. And actually, before that time, that was in the 4th century, people also managed to do something interesting or useful by taking advantage of this optical phenomena of nanoparticles. And basically what's happening, this is so-called surface plasmon resonance of nanoparticles. You have a high density of free electrons that can respond to the electric field of light and to have collective oscillation. And then you are going to have light scattering absorption at a specific wavelength referred to as localized surface plasmon resonance. And you can have very strong absorption or scattering depending on the size of the particles. Typically for small particles, absorption will be in dominance. And absorption could be very, very strong. Typically, if you look at the cross-section, one particle of this size is the equivalent of maybe 1 million dye molecules. So you can see the scale difference. Anyway, for this gold-based nanoparticles, they have found quite some interesting applications in biomedical field. And some of these arguments for gold, as I mentioned, the gold is not a biodegradable material. If you put the gold in your body, it will stay there forever until you die, probably. Okay. So in this case, it's something that's good and bad. The good is it's bio-inert. It's not going to trigger any bad responses. And at the same time, you won't be able to get rid of them once it's inside. Okay, so that's basically a fact we had to accept. But gold has an array of interesting properties, including this gold thiol chemistry that has been established over past several decades. And this can be used to functionalize the surface of gold and for targeting purpose, for other applications. And also gold can be alloyed with different elements and give you other functionalities. Okay, this can include magnetic and other features. And also even you can think about gold they have their radioactive isotope that can be easily used. And this can also give a chance to do imaging and also radiotherapy, actually. Okay, so basically, gold has a range of unique properties eventually could be used for biomedical research. And in terms of synthesis, there are thousands of papers out there. Okay, I just want to highlight a few. Basically, you can make, for example, gold nanospheres with a very broad range of size, with very uniform size. And here just something we developed a few years ago using this seeded growth. If you're interested in detail, you can look at this paper. You can make them very uniform size form, all the way from 5 nanometers to hundreds of nanometers in this case. And the uniformity is also very good if you look at variation of coefficient. Typically, we can call them kind of like a monodisperse, even though we don't call it. Okay, so these particles are good and unique because you can think them as like a model systems. Okay, to investigate how nanoparticles will interact with cells when they have different sizes, when their surfaces are presented with different functional groups. So it's a very unique system to do this kind of studies. And most of our research has been focused on a different version of nanostructures, like shown over here, we call gold nanocages. The difference is that it's hollow. Okay, it also has small pores on the surface, and different from the solid particles, we can easily tune their surface plasmon resonance peaks into the near-infrared region. So that's basically important for biomedical applications. So now we can easily make them using a simple chemical method called galvanic replacement. You have silver nanoparticles formed, and then you mix with gold ion solutions. You can make these gold nanocages. At the same time, you generate soluble ion species of silver. And you can do like a titration. You can generate structures with well-controlled shell thickness. So that's why how you can precisely control the absorption peak positions. And for biomedical application, I didn't emphasize, it's important to use light in this wavelengths, in this window of wavelengths to achieve deep penetration. It's called near-infrared transparent window. Okay, so for nanocages, it's very easy to reach this region, but for solid particles, most of them are going to be in the visible region. It's not ideal for imaging, for light-triggered applications. Okay, but for other applications might be okay, in particular for like in vitro purpose. Okay. So we have systematically evaluate the use of these nanocages for, like, for example, cancer treatment without using any drugs, just using this nanocage themselves, because they can convert light to heat and generate a hyperthermia condition and cure cancer cells. So we have done a set of studies. We can see the efficacy, and we also have confirmed using like some imaging modalities. Anyway, I don't have time to go through all these details. And they can also serve as contrast agents for imaging application. In this case, it's for photoacoustic imaging because they can absorb light, convert to heat. So that's a very effective way to create a contrast for photoacoustic imaging. And in this particular study, we have compared two major mechanisms for cancer, for tumor targeting. One is called passive targeting, another is called active targeting. So basically, for tumors, you are going to have leaky vasculature. So nanoparticles will be able to leak out when they flow to these regions. And this is something we call passive targeting. Once they leak it out into the tissue around the tumor cells, they may have low chance to go back. Okay, so you are going to have passive targeting mechanism. For active targeting, these particles are going to be further functionalized with some functional groups. Basically, they can bind to the receptors on the cancer cells, and they won't be able to go back anymore because they are going to be anchored to the surface of cancer cells and then internalized by cancer cells. So this is called active targeting mechanism. Basically, as you can see over here, this is based on the melanoma tumor model. For passive targeting, the accumulation of these particles inside tumor is relatively minor. But if you have this targeting ligand, it's a short peptide we put on the surface of these nanocages, the enhancement of signal is quite significant. Okay, basically the difference between them could be almost like 3 times to 4 times actually. Okay, so you can see the difference between passive targeting and active targeting in this particular case. And yeah, since these particles are hollow, so you can put the drugs inside, you can have them released. In a recent study, we put this unique organic compounds inside. This is basically an initiator commonly used for radical polymerization. Basically, you can easily generate free radicals. And these free radicals actually can be generated on site inside the tumor, and eventually, basically, they can serve as a role or like ROS, reactive oxygen species, to kill cancer cells. And for photodynamic therapy, actually, the reactive oxygen species is very important, but it has to rely on the oxygen. But unfortunately, for solid tumors, the oxygen level typically is low, so it's going to be an issue. So in this case, by delivering this particular compound into the tumor and then you trigger the release, actually we can have more effective way to kill cancer cells without relying on the diffusion of oxygen in general. I don't have time to go through all the details. If you're interested, I suggest take a look at this publication. But again, this is just in vitro study. We haven't been able to test this in vivo. And finally, if we can form an additional layer of another matter, in this case, is a mixture of copper and gold. We can functionalize this particle to move this one step closer to clinical use. And the idea over here is to think about the copper-64. Copper-64 is an isotopic tracer that can be used for PET imaging. So basically, if you can incorporate them into nanoparticles, you will be able to see where they are going to be located, at what time, and at what concentration. So basically, it can give us opportunity to do image-guided therapy. Okay, so that's a new development. Basically, we can put a thin layer of gold and copper on the surface, and some of the ordinary copper could be replaced by copper-64. It just makes the right precursor. So you can have them radioactively doped, and then you can see them by PET imaging. Okay, again, don't have time to talk about details, but we can really locate where these nanocages are located, are positioned, and what kind of concentration, and so on and so forth. So that will give us eventually a useful platform, okay, to move toward clinical evaluation in the future. So finally, as I promised, I want to show you some challenges in this area. I have shown you some very nice studies, but most of them, I have to say, is not really close to clinical use yet. Okay, one of the major issues, it's not the issue, it's really the mother nature, actually, okay, the complexity of biological system. And when you talk about internalization of nanoparticles, depend on the size, shape, and surface functionality, the way they are going to be uptaken by cells is going to be quite different. They have quite different mechanisms. But unfortunately, in literature, most people didn't pay much attention to all these kind of details. They just say, oh, okay, this particle is uptaken by cell, by what mechanism, and how you are going to manipulate it. It's still not very clear. So maybe in the future, people will pay more attention to this particular aspect. And the other challenge is still, this is particularly related to clinical translation. This is about biodistribution and pharmacokinetics and so on and so forth. And I didn't show you this plot. Okay, actually, in many cases, when people publish paper, they don't want to show this because this is bad data in a sense. You can see most of the nanoparticles, no matter what kind of shape you have spheres, discs, rods, cages, whatever. Majority of them are going to end up in these 2 major organs, liver and the spleen. Okay, so not necessarily the diseased organs you want to damage. Okay, so this gave us some kind of like challenge, okay, how we can avoid this, right? So that's something still under extensive research, but now still there's no exact solution, okay, available. Okay, maybe in the future you guys can find interest to look at this. And of course, surface modification probably can play a very important role. But at the same time, we need to spend more efforts to invest in this, how we can improve this. And the reason they get into liver and the spleen, because this is our immune defense system. Actually, you have phagocytes that will uptake these kind of particles and drag them into these two organs. And in a sense, in the future, this is just two final figures I took from the review article I mentioned earlier. This is about like a comparison of cytotoxicity. This is mainly for in vitro, of course, and also liver accumulation and also tumor accumulation and so on and so forth. And these are going to have very strong dependence on the physical parameters of the nanoparticles, including the size and shape, surface properties. So basically in the future, maybe for each system, for each disease, you need to have a systematic study to optimize each one of these parameters. And eventually, you can only deliver these nanoparticles loaded with drugs into like tumors, actually, okay, and instead of everywhere or healthy organs. So that's probably will be the ultimate goal. Actually, we call this maybe a magic bullet, okay, that can eventually used for to fight cancers. So with that, I just want to stop and thank you for your attention. More than happy to answer your questions. Thank you. Sure. Okay, so yeah, her question is about chemical activity of copper. Typically, they can be oxidized or destructed in aqueous system. So basically, in this case, we use a very low concentration of copper. It's like alloyed with gold. So of course, their reactivity is going to be reduced significantly. At the same time, if you want, because in our study we didn't observe this kind of issue, so we didn't further modify our protocol. If needed, you can coat another layer of pure gold on the outer surface, and then you can have better protection, okay, against the oxidation and so on and so forth. So yeah, work with metal is much more flexible in a sense. You can think about all different formulations you want. These metal atoms could be easily mixed at essentially any ratio. Basically, they can form alloys very easily. Yeah, so that's basically one of the problems and solution. Okay. Okay, so her first question is how we can functionalize liposomes with the targeting moiety on the surface. Well, you can do in a number of different ways. Typically, when you make this kind of lipids, you can use different mixture of different types of lipids. Some of them might already have functional group attached to it, or at least you have some functional group. You can further attach something to it. Okay, after you have formed this liposome. Okay. So that's the best way. You can use conjugation. You can use covalent coupling and so on and so forth. Another way is also possible, I think. Once you have formed this liposome, you can have some lipid exchange on the surface. If you mix this with another formulation of lipid system, they may have exchange between them. You can also introduce functional group to it. Yeah, so there are a number of different ways you can do it. First, repeat your question. How we can load drugs inside the nanocages and have them released afterwards.
These are gold nanocages?
These are gold nanocages. You have pores on the surface, allow you to load things inside. And once they are loaded inside, you solidify them. Typically, we load them at temperature above the melting point of the PCM. And then you reduce temperature to solidify. Everything is going to be trapped inside. And then when you do release, you have to heat up the particle. We typically use a photothermal heating, and then you can trigger the release. Once the PCM is melted, they're going to come out by themselves. Yeah.
Thank you.
Mm-hmm.
Well, in the interest of time, I think we'll move
All right.
on. So, thank you.
All right, thank you. I will be around anyway.